VSEPR, or valence shell electron pair repulsion theory, is a simple but really useful theory to describe a molecule shape. It states that a shape is determined mainly by minimizing electron pair repulsions, which is done by keeping all the things around a central atom, or the regions of electron density, as far apart as possible, because they all have negative charges that repel each other. You can get really far with just that first key principle here, but in certain cases we also need the second key rule, which is that lone pairs repel more than bonding pairs. So lone pairs are going to stay as far apart as possible from each other and from any other electrons if we ever are unsure of where a lone pair should go on a central atom. With these simple rules in theory out of the way, how the procedure works is pretty simple. We first have to calculate the steric number for our central atom. That is defined in this precisely worded way as the number of bonded atoms plus the number of lone pairs around that particular central atom. Once we know the steric number, the electron geometry, or sometimes this is called the bonded atom or lone pair arrangement, is determined by just figuring out which shape is the best way to keep that number of things as far apart as possible. Then once we look at the lone pairs, the molecular shape will come from just the shape that the atoms adopt, since the lone pairs won't be visible. They'll just influence the geometry of the atoms, which we can see. Just to reiterate one key point, the steric number is precisely defined as bonded atoms plus lone pairs. So something like CO2 just has a steric number of 2 bonded atoms. So 2 bonded atoms plus 0 lone pairs on that central atom. Even though these are multiple bonds, it's still just 2 atoms bonded to the central carbon. And a second point, it's only the central atom we need to worry about. So that's a common thing that people miss in VSEPR theory. Even though those multiple bonds contain more electron density, it's still just one region of electron density, or one place to put electrons, which is one good way of thinking of the steric number. Okay, so now we're going to build this VSEPR table that connects which steric number relates to which electron geometry. Remember, the idea is that we keep things around the central atom as far apart as possible. So for 2 things around the central atom, which I'll represent with an E here, the best way to do that is to arrange them in a linear type of shape. That keeps them 180 degrees apart and is the best way to keep 2 things as far apart as possible. If we change these angles, they would get closer together. And again, this is called linear. Similarly, for 3 things, the best way to arrange 3 things in space to keep them as far apart as possible is to arrange them in this trigonal planar geometry, which has, again, a circle divided in 3 now, 120 degree angles. Sometimes people worry about memorizing these bond angles. There's only one sort of weird one to remember here, but this is a circle divided in half, 360 over 2. This is a circle divided in thirds, 360 over 3, or 120. Again, coming right out of just the basic shapes that we get here. For 4 things around a central atom, it turns out that that shape is a little bit more complex. That's going to be this familiar tetrahedral shape. Where we now have to sort of worry about the 3 dimensions, which I'm trying to represent with these little solid and dashed lines to represent something coming out of the page at us and going back into the page. The tetrahedral angle here is sort of a weird geometry problem. This happens to be about 109 or 109.5 degrees, the angle between each of these different points of our tetrahedral. Then for 5 things around the central atom, it turns out that we're back to basically putting together a 2 and a 3. So we basically have linear up and down here. And then in the plane of the page, it turns out that the best way to arrange these things is in sort of a triangle here. So for 5 things around the central atom, we have a shape that looks like this. We have 90 degree angles here going up into this plane, and then 120-degree angles here in this triangular shape in the plane of the page. This is called, if we think about what this shape would look like if it were solid, this is trigonal bipyramidal. Then when we get all the way to 6 things, this is back to a very simple shape, sort of the 6 faces of a cube, up, down, front, back, left, and right. So 6 things, all 90 degrees apart in an octahedral geometry. So again, these 5 shapes are our only possible electron geometries, and as soon as we count out the steric number, we can immediately say what that basic electron geometry is, and we can largely also say what the bond angles in our molecule are going to be as well. So just from the steric number, we get quite a lot of information about the molecule. Here are those same shapes in a little bit prettier type of 3D pictures. You can see what they all look like. And these will be your molecular shapes if there are no lone pairs around the central atom. Again, the molecular shape is just the shape of the molecule, and if there's no lone pairs, it will have the exact same name. So these are examples of molecules here with no lone pairs around the central atom who have these given shapes: linear, trigonoplanar, tetrahedral, trigonal bipyramidal, and octahedral. So now that we've done some examples of simple molecules that have no lone pairs, let's start adding some lone pairs in. So the next thing we'll do on this table is build in the case where we have, say, 1 lone pair, and then, say, 2 lone pairs. In theory, I guess we could even have 3 lone pairs. That's the case for a few of these bigger geometries. Okay, so let's start filling in some of those geometries. For 2 things, a lone pair is pretty boring here. Then we just have only 2 things, which is always linear as well. So we get interesting things going on here, starting with trigonoplanar. If we have something that has a steric number of 3, but one of those 3 things is a lone pair rather than atom, then we get something that looks like this. A lone pair X, X. And now, again, the shape here, we don't see that lone pair, so we just see this bent shape is what's left over. Bent with a bond angle of 120 degrees, actually typically a little bit less because of our rule that the lone pair takes up a little bit more space than everything else. So a slightly less than 120 degree bond angle and a bent shape for 3 things with 1 lone pair. If we do 4 things with 1 lone pair, now we go over here, we have A, X, X, X. So one of these spots here is our lone pair. Let's put it right up there. And the remaining shape here is not in a plane anymore. It's making this sort of pyramid shape with 3 legs. So this is a trigonal pyramid shape. And again, the bond angles are sort of less than 109 degrees because that lone pair is pushing everything else a little bit further away. Now, the other really common geometry here is with 4 things, we could also make 2 of those 4 things around the central atom's lone pairs. So I'm going to put them in these 2 positions so our remaining molecule looks in the plane here. So again, I've got now A, and I'm going to put 2 lone pairs over here. And what we can actually see is this part, A, X, X, those are the atoms. And that's, again, going to be sort of a less than or maybe a good bit less than 109 degrees because we've got 2 lone pairs pushing these 2 atoms closer together. And this is bent as well, though bent with a different bond angle than if we had a steric number of 3. This bent has a slightly lower bond angle. These are the really common shapes that you see all over in sort of all areas of chemistry are these normal 2, 3, 4 steric number shapes, bent trigonal pyramidal, tetrahedral trigonal planar, linear, very, very common. There's a lot of other shapes in the rest of this table, so we'll just go through those. For trigonal bipyramidal, if we put one thing around it, we get this sort of shape. This, again, the bond angles are maybe like less than 90 degrees, less than 120. And this shape, if you sort of tilt it on its side, it would look like a seesaw. With two lone pairs, and again, because the lone pairs occupy more space, they always go in these equatorial positions where they have 120 degrees to these neighbors. So I'll put those lone pairs here and here in those two positions. Then I have A, and what's left is X, X, X. Again, if I think of sort of tilting it on its side, this, if you look at it sideways, is a T shape. So that's T shape. We could add a third lone pair on there. That would take up that last spot, and we'd just have a nice linear shape there with three lone pairs. So it sort of comes full circle all the way back to our really simple linear geometry there. With octahedral now, again, if we put there, we don't have this issue of like axial versus equatorial. We just have all these positions being the same, so I can just sort of arbitrarily shove our electrons in some place convenient for me. If I put that first lone pair down, I get this geometry with one lone pair. This, if we look at it, has a nice sort of pyramid-y shape, but we've got four things on it, so that's a square pyramid. Again, still roughly those sort of 90-degree bond angles. And again, if we put a second thing around the central atom, that would go up here and would just leave me those four things right in the plane. So this then would just be like A, X, 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 X. I don't even need to try to draw this 3D because this is perfectly in the plane, and this is square planar with exactly 90-degree bond angles. If we added a third lone pair, that would take up like one of these spots, and then we'd actually be back to our little T shape, the same as here. So that's all the different geometries. You get really far by just knowing these basic electron geometries. That always gives you the bond angles and the electron geometry, and if there are no lone pairs, the molecular shape as well. If there are lone pairs, then you have to sort of remember some of these slightly odder geometries, especially over here. Definitely, memorize your bent, trigonal, pyramidal. Those come up a ton. These are just a little bit harder to remember, but you should note that octahedral always has these sort of square shapes, and trigonal bipyramidal, when you take one away, turns into this seesaw shape. Take two away, take two atoms away, and replace them with lone pairs, you get to a T shape there. And that's really basically it. So this is all you need to sort of know. This big table that we went through has all the information that you need. It is maybe, a little bit of an issue just remembering the names of these different shapes. Definitely, think through those and try to remember those as well as you can. But if you have this basic picture of steric number, electron geometry, and then just fill in the lone pairs, know your bond angles, you'll really be in really good shape for this exam. Yeah, this is that overall process. You need the Lewis structure first because you need to know about the lone pairs. Steric number, add up bonded atoms and lone pairs. Then use that steric number to determine the electron geometry. And then fill in those lone pairs to determine the overall molecular shape.